Hello, hi, Hannah. Good afternoon, Noreen. Where I see Hannah, but I don't see Hannah. How did you do that? Wait a minute. Oh, and good afternoon, Kazi. A good thing. Okay, wait. Okay, I'm going to do this correctly. Sorry, and sorry I'm late for even being late. Ooh, that's gunfire. Hello, oh, and I'm sorry, and Quan like totally came. Okay, hello, Quan. I totally missed you. Hi, Hannah. Totally still missing you. Wait, how's Hannah doing that? Wait. Oh, I see. I'm sorry. Oh my God. Okay. Hello, Shasha. How are you doing that? I don't know what you're doing. Good afternoon, Noreen. Hello, Almadina. Good afternoon, Kazi. I'm apparently a crazy person. How are you? Hi, Kareem. I guess I'm a crazy person does not really answer how I am. It answers more like what I am. Hello, Grisella. Okay. Hello. Oh, and did I say Adriana? Did I say? Oh, okay. Hello, and oh, hello, Yulia. And hello, Adriana. Hello. All right, this is, you know, I can, you can imagine, in a restaurant, I'm a nightmare. Like I can get confused over when they come to take our water order. Okay. Wait, restaurant? What's a restaurant? I feel like I remember being in a restaurant like 2 years ago before COVID. Anyway, okay. Hello. All right, so I'm late for being late. We actually do have a action-packed class today. Not that. Oh, in fact, oh, pardon me. More delay. Wait, I thought I just saw it. All right, let's see how many different. In our study of sound today, I'm going to change the octaves of my voice 14 more times. Excuse me for a second. And okay. And please ignore the wizard behind the curtain. Hang on a second. The thing that's happening on the screen right now is not meant to be relevant to our lives. It's just happening. Public. It's like getting electronically undressed in public here. Sorry, which is not an appropriate thing to say at all. Pardon me. Okay. Pardon me. Oh, for heaven's sake. Okay. Pardon me for a second. Talk amongst her. This happened last week too, didn't it? Yes, it did. All right. Let me tell you what we're going to do today. Let's get ready to do what we're going to do, even while I embarrass myself even more than usual. We are doing the Doppler effect today. Oh, someone else is here. Last time we were about to start doing the Doppler effect, and we got into what I do feel was a very interesting, rewarding kind of conversation about sound waves themselves. I was into it. I think you could tell I was into your questions. I think it was valuable. I hope it was valuable, but it was sort of it ended up being a general discussion of sound waves. Today, I want to be more specific and mathematical and analyze a phenomenon that occurs with sound, a phenomenon that occurs with all waves, but most familiarly with sound waves. It's called the Doppler effect. That's what we're going to do. We're going to do at least one case of the Doppler effect today. If you just indulge me for 1 minute and I get my act together and fix the board situation here. So bear with me for 1 second. That's a please. And literally, out of curiosity, do you guys hear that? That's that gunshot. Do you hear that? Did anybody? No, you can't hear.
I heard that.
You did hear it for real? That's pretty crazy.
Yeah.
It's pretty crazy, right? Like that is. Oh yeah, no, I am. And no, I'm safe. Well, I'm not. No, I'm safe. So I'll tell you in a second. But thank you for asking. I'm totally safe. But that is totally gunshot, and you will hear it again. But that really is gunshot. Yes. here's the, but I am safe. It's not, that's, I'll tell you in a second, well, both, like why both statements are true. And you'll hear it again, I'm pretty sure. Okay, hang on one second, sorry. Oh, come on. Well, I'm safe from that anyway. I don't know if I'm safe from like myself or from electronic devices. Good heavens, come on, yo. Just trying to make a living here, for God's sake. Can't a guy make a living? It's a funky way to do it.
Professor,
Yes.
are you sharing your screen?
I'm trying to. That's the problem. Thank you for asking. I'm having difficult. I'm not successfully sharing my screen yet, but I'm trying to do something on the screen to get it back. So that's why no. But thank you for asking. You're absolutely right. That's the delay. It's a great question. Okay. Okay, we're just about to. Your tone was so polite, though. The way you asked that, I literally thought you were about to say, like, Professor, are you aware that you're on video while you're embarrassing yourself like that? Or something like, are you aware that we can see truly how crazy you are? Are you aware? Like, I thought you actually knew, for example, that I've been teaching physics on Zoom in jacket and tie and pajama pants for about 2 years now. And that's no joke. Hold on. All right. Okay, we are just about there. I believe problem has been solved. I believe we'll see in a second. I apologize. Yes, every one of your tuition dollars is being. Okay. It's being devoted to this cause. Okay. Okay, the screen should, yes. Okay, okay. Okay. Okay, here's, okay. Sorry about that delay. Thank you for indulging. Great, thank you. Thank you for that feedback. That's great. I feel like I exist. Thank you. I told that's like major points. I appreciate it. Okay. Oh, and yeah. Oh, good question. Sorry, that's a very fair question, Hannah. It has been a while since we do have to. To be honest, I'm not sure that was my plan for today, partly because because we got in the middle of this other thing. I think, sorry, that's a very fair question, but the honest answer is I think that we're going to do that next time. Oh, okay. Yes, totally. But thank you for the reminder. Fair enough. Yes, we are. And probably next time. Now, especially now that you reminded me. Okay, thank you. And that's points for closing a conversation. Thank you for making me feel like a human being again. But yes, and thank you for reminding me. Okay, what we're going to do today, however, is analyze the Doppler effect. And I will say, by the way, like, so I don't teach from New York City anymore. I teach from Maine, from a small town that is north of Portland, Maine. And that gunshot that you're hearing is not like Brooklyn neighborhood gunshot. That's hunting season gunshot. That's how I know I'm safe, because I'm in the house and wearing orange. No, but I've never lived in a place that had hunting season before, but yeah, I guess. I mean, it certainly is interesting. I mean, it's literally like a thing where I live now, or where I live now. Like, you actually have to like wear bright orange hats and things when you go out in the middle of even the day, because we're near enough to the wood. Anyway, I've never experienced it before, but yes, hunting is occurring. Oh, cool. You do. Oh, they're kind of, okay, cool. Oh, that makes me feel a little bit better because it is news to me. Okay, where up? Oh, I thought. Oh, okay, cool. Well, that makes me feel better. Great. Okay, then good. The thought of danger does not cross. Okay, I've got to ask, so where upstate? Did you, or if you don't mind my asking?
I grew up in a really small town, kind of near Ithaca.
Oh, wow, really? Oh, wow. Okay, good for you. Okay. Wait, what's the town? Okay, well, anyway, okay, great. That's very cool. So now I feel safer. Thank you. Okay, we're going to do the Doppler effect now. In fact, we're going to get, okay. Remember, background for the Doppler effect. One thing I do want you to remember from last time, since we spent so much time talking about it, in the back of your mind, remember that when you experience sound waves, remember frequency of sound wave we experience as pitch, like highness or lowness with respect to like to note, and amplitude is what we ultimately experience as volume. The Doppler effect is all about frequency. Okay, so it's all about pitch. I'm going to write down what specifically the Doppler, and again, the Doppler effect applies, and this is important to realize, it applies to any waves of any kind at all, but it's very, very familiar and common and reliable and vivid when it comes to sound waves. So, okay, first I want to say as clearly as I can, like we're about to study the Doppler effect, right? I'm not even yet saying what the Doppler effect is. I mean, you might sort of intuitively already know, or you might not. I'm going to say what the Doppler effect is. I'm going to describe what the effect is. But before I even say what the effect is, I'm telling you what the condition for the Doppler effect is. In other words, I'm telling you when it will ever occur, or sort of why it will ever occur. So the Doppler effect occurs or arises when you have a wave being transmitted, a wave of any kind being transmitted from what we're going to, from here on in, call a source to, let me start again, sorry. Waves go from things to other things. From here on in, we're going to call whatever sends out the wave a source, and we're going to call whatever gets the wave, we're going to call it a receiver, kind of like a speaker and a receiver, right? A source and receiver. If either the source of some wave or the receiver or both have any velocity at all relative to the wave's medium, then we get what's called a Doppler effect. I mean, then we will observe what's called a Doppler effect. Let me say it again, or let me say it a slightly different way. I'm saying if I send a wave to you, oh, no problem, thank you. Oh, and we went public, thank you. Hello, good to see you. You missed nothing, just me being hunted or something. So if I'm a source right now, I'm sending sound waves to you, and again, forget the internet part of this. Like just pretend you and I are in the same room, just okay. And I'm sending sound waves to you, so I'm the source of sound waves, and then you're hearing them, so you're the receiver of sound waves. the sound waves, if they're waves, they must, by definition, be traveling through a medium, right? In this case, if we were sitting in the same room, the medium would be air at standard temperature and pressure. If either or both of us are moving relative to the air, if either or both of us are not stationary, not at rest relative to that air, then a Doppler effect will occur. Let me also, so again, it's either or both of us. Let me add to that. I mean, so remember, we're going to be focused like heavily. This whole phenomenon requires that we understand wave motion, but also requires that we understand motion in general in the first place. It's going to require us to really remember and embrace and deploy the relational character of velocity. I'm going to remind you what I mean by that, but all velocities are relations between pairs of objects. Velocity is never a property of a single object. It's a relation of one object to another. This is called Galileo's principle of relativity. And we're going to bear that in mind heavily as we investigate this phenomenon. And when I say bear it in mind, part of what I mean by that is right here off the bat, when I'm saying if either a source or a receiver has velocity relative to the medium, that's equivalent to saying if the medium has velocity relative to the source or the receiver. Velocity is relative. So I'm basically saying if I shout to you while either I'm moving through the air, like running toward you, or you're moving through the air, like running toward me, or you're running away from me through the air, or let's say the air is moving past you or past me, i.e. wind, any of those combinations or permutations or examples would produce a Doppler effect. If there's any relative motion at all between any agent of the wave and the medium for the wave, then we get a Doppler effect. And so what is a Doppler effect? That's the next page. Rephrasing. I love when you guys do this. Rephrasing is so good. Very good. Okay. I'm glad Quan just put that. So as long as we're being as clear as we can be and we're rephrasing, I'm actually saying the source and or the receiver. It doesn't have to be an and, it could be an or. Like in fact, if you're going to use any one word, I would say the better word is or. If either the source or the receiver is not stationary, that's good enough to make a Doppler effect. Okay, but I also have to, and I am glad you're being clear about this. We do, oh, cool. Okay, and to everybody on Quan's like clarification and on my clarification, I also, you'll see, I have to be very clear, like as a physicist, I can never really say that anything is stationary. And I don't mean this just as like a technical point. I mean this as a very real point. Like things are not just stationary or not stationary. Like, is the Earth stationary? Well, the Earth is stationary relative to itself, but it's moving relative to the sun, and et cetera, right? So like there's no such thing as anything being absolutely at a given speed or absolutely at no speed at all. So to be proper about this, I have to say if either the source or the receiver is not stationary compared to the medium, that's the key here. It's going to be all about comparisons to the medium. So for example, well, so you'll see, but yeah, but other than that correction, yeah. All right, so now what is the effect though? What will happen if And this is a very big deal. Like most big deals in physics, at least in my experience, are simple, not easy, but simple. This is a simple point, but it's a very big point, and it has very complex implications. The Doppler effect itself, what the Doppler effect is, it is a disagreement over frequencies between the source and the receiver. When I say disagreement, I don't mean argument like their opinions are different. I mean they're differing measurements. I'm saying that when a Doppler effect occurs, if the source makes a measurement of the wave frequency and compares that measurement to a measurement made by the receiver of that wave frequency, they're going to get different measurements. I'm saying if it comes to sound, the source and the receiver are going to literally experience in every real way. They're going to experience, observe, measure two different frequencies. I'm saying more, and neither one of them is going to be in error or something like that. It's not going to be a matter of mistake. It's a matter of frame of reference. So I'm, for example, saying, so one example is like the classic example is is like motorcycles down the street or sirens and ambulances, or I suppose gunshots if they're done correctly. Like the Doppler effect is this business. That's the Doppler effect. But let me be very clear about, let me try to be very clear about that. Like there's a lot of things actually even going on in that. And when I go like this and make that stupid motion, I'm simulating like as though you were standing on a New York City street and a motorcycle approached you and then passed you. Or even like a car that was honking its horn and you hear like, whether it's from the horn or the car itself. Now, let me be clear about a couple of things. First of all, I'm not talking about volume here. I do understand that as objects get closer to us, they tend to get louder. And as they get farther away, they tend to get softer. That's true. That is not the Doppler effect. That's logical. It makes sense. It happens all the time, but you don't need any special conditions for that to happen. Things get louder as they get closer, they get soft. So I'm not talking about volume here. I'm talking about frequency. And I'm also not talking about position. I'm not saying at all that when a motorcycle is like far away, it has some low frequency. And then when it gets closer to me, it has a high frequency. That is not what I'm saying, because that's not true. I'm saying that as a motorcycle is coming to, let's just say it's a car and someone's honking their horn. So let's try to keep this simple, right? Let's say someone's in their car and they're pressing their horn, and their horn is like just a solid sound. It's not like a siren, right? So let's say their horn is just like a, now I don't have perfect pitch or anything like that, but let's just say that their horn is like middle A on the piano, or middle C on the piano, 256 hertz, right? So they're pressing their horn, 256, in fact, well, maybe I'll do it in a second, but I do have something to make sound, but so it's coming towards, so they're playing the sound 256. Now they in the car hear, and if they had like a pitch pipe, or if they had measuring equipment or like a stroboscope or something, an oscilloscope, I mean, they could measure and they find out, there's my C, that's a middle C, it's 256 hertz. Great. Okay. Now, if you were in the car, you'd experience the same thing. If the car were sitting still in a parking lot and you were standing anywhere in the parking lot, you would experience the same thing. I don't care how far away you are or how close. If you're standing in the parking lot and the car is in the parking lot and they play a C over here, you would hear a C over here. What I'm saying, though, is that if the car is coming toward you while it's playing that C, if the car, or more specifically, if the car is moving through the air being the medium through which that C has to travel to your ear, if the car is moving through the air while it sends that sound out through the air to you, then what you're going to experience and what the car people are experiencing are two different things. I'm saying that if the car is coming toward you while it plays this C, while it plays this 256 hertz frequency, you're going to receive a higher frequency than 256. Yeah, that is true. And let me get to that in a second. But yes, Hannah, yeah. Yeah, before that, you're already at like the hard part, but yeah, but wait. Yeah, totally. Well, actually, no, that's even a better question than I thought. I underestimated that question. Hold on a second. I still want to continue this, but yeah. Oh, yes, totally, totally. No, Hannah's question. I will address it to everybody, but yes, Hannah, like totally, that's the point. So but I'm going to just break this down slowly for a second there. But yes, if something's coming toward me while it's playing that 256, according to it, I'm not going to hear 256. I'm going to hear something higher. And my measuring equipment will register something higher. And I'm not being fooled. It's the reality of my reference frame. I would hear something like 300. If they were going away from me, I would hear something lower than 300, which gets to Hannah's question in a moment. But I want to say this to everybody now to be as clear as I can. We're going to run the math. Like there are mathematical implications, there are all kinds of implications. We're going to do the example with numbers in a second. But I just want to get the concept out there. We're talking about something that has everything to do with motion and the relativity of motion. We're not, and this is, again, this is sort of like the point of Hannah's clever like separation of variables like arrangement that she just came up with. Like this has nothing to do with geography. It has nothing to do with where things are, and it has nothing to do with volume. It has to do with the fact that sound travels as a wave. So I want everybody for a moment to picture if you were at the beach, like with ocean waves for a minute, right? Say you're at Far Rockaway or Coney Island or whatever, and water waves are coming in, like say like one every second, like, you know, that's their frequency, 1 hertz, just to make up a random number. If you're standing at the beach and watching these waves, then the waves hit you 1 every second, right? And say that someone's here, sorry. Like, and I'm saying, say they were sent out from a big ocean liner or from some natural event in the middle of the ocean, or whatever, like they were sent out at 1 per second. And if you stand at the beach, they would hit you with a frequency of 1 per second. But if you imagine, if you start running toward those waves, right? Like from the frame of reference of anybody who made the waves or who said them, nothing interesting has happened. They don't care that you're running toward the waves. But if you're running toward the waves, they're going to hit you more frequently than 1 every second. I mean, I want anybody to stop me if they can't picture that, or maybe even put in the chat if you do picture what I'm saying. I'm saying if you are stationary relative to the water as the ripples come in, you'll receive the ripples at a frequency that they were sent at. But if you're running toward, if you're literally approaching the waves or the source of the waves, you're going to encounter them more often than if you were just standing still, because the waves are separated by a certain amount of time. They have a certain period, 1 every second, but you're helping out. You're like, instead of waiting for the very next wave to come, you're like running toward it, closing the gap, shortening the amount of time that has to occur before it hits you. So you would literally be increasing the frequency by at which they hit you. And if you, same idea, if you run away from the waves, they'll hit you less frequently. And it wouldn't be an illusion. It wouldn't be a mistake or an error. It literally just is what's happening in your frame of reference, in your perspective. What I'm saying is that if there's, and similarly for that matter, say that these are ripples like in a pond or something. If someone shoved the whole pond to you, like while you're standing there, then you'd get the waves faster than if they didn't shove the pond to you, if all the waves are necessarily going at a certain speed relative to that pond. So I'm saying if there's any motion at all of the source or the, and the example I was just doing was the receiver, but back to the street, the example I was just saying, if you were on the beach, that analogy is all thinking about what would happen if the receiver approached or receded from these waves. And I'm claiming that if the receiver was approaching the waves at some non-zero speed relative to the medium, then the received frequency would be higher than the source frequency. And conversely, if the receiver were going away, the received frequency would be lower. Now, going back to the street, and I will get to Hannah's thing, I do love it. I did underestimate it at first. I'll get to it in 1 second. But going back to the street now, I'm saying it's the other side of the analogy. If you're standing around being the receiver and there's some car blaring a horn, if the car is driving toward you while it presses on that horn, that is an approach. That means that the thing making the waves is getting closer to you, is moving toward you while it's making the waves. My argument is, I don't know if that's as easy to picture as the thing at the beach, but I'm saying it's the same concept. You're going to encounter those waves more frequently than you would if the car were just sitting still. The truth of the matter is, we'll see in the math in a second, if that's hard to picture, we'll see in the math in a second that if the car is moving toward you as it produces waves, what's happening is it produces one little peak or one little crest, one little wavelength thing, and it has to wait a certain amount of time to produce the next one. But if it's running toward while it's waiting to produce the next one, then those crests are going to be closer together than they would be if the car were just sitting still. In other words, by the car approaching you, it's actually compressing the wavelengths. And if all waves have to travel at the same speed relative to their medium, if you make a smaller wavelength, you necessarily get a greater frequency. Those ripples will now ripple at you more regularly, more frequently than they would if the car were sitting still. So the long or the short and the long of what I'm saying is, if in the car, if relative to the car, it experiences a 256 hertz, if the car is approaching you at some speed, you're going to experience higher than 256 hertz. And the faster the car is going, the more higher you're going to experience that frequency, the more dramatic a Doppler effect there will be. It doesn't matter where the car is, and I'm not talking about volume. It's just, so if the car goes at constant velocity, I'm not saying you're going to hear, and okay, now here's where Hannah's question comes in. If the car is coming toward you at constant velocity, I'm not saying you're going to be hearing an increasingly like more and more and more frequency. I'm just saying you're going to hear a higher frequency than what the car hears if it's coming toward you at constant velocity. Then when it passes you and it's going away from you, now it's going away from you. So now you'll hear a frequency that's lower than what the car hears. The car will hear a constant frequency. You'll hear a constant frequency, just lower than what the car hears. So then Hannah's question is a perfect one because it's sort of getting at, it's like distinguishing, right? I believe, if I'm understanding it correctly, it's really trying to highlight how starkly I'm saying this is about velocity and direction. It's not about position, because her point is, if a car was directly in the middle of two people and is moving toward person A, the sound wave of the horn would have a higher frequency for person A than it would for person B, even if the car is in the middle. I mean, that is, sorry, I'm trying to read it out loud. I hope everybody can see it. That is dead on right. Like, that is a perfect question. Even if a car is in the middle between A and B, even if it's equidistant from A and B, if it's going toward A but away from B, that means A is going to hear a higher frequency than the car will, and B will hear a lower frequency than the car will. That is dead on right. I mean, again, great. How many times can I say this? But great question. And please, submit for 8,500,000 points. Now, cleverly, if anybody else in the class just says, "Oh, Hannah, that's such a cool question," or if they say like, "Oh, I get it," then they get points for doing multiplayer co-op, and so does Hannah. Right? Just saying. Anyway, isn't it a friendly world we live in? But so that's why the Doppler, so we're going to do the math now. I want to, and again, this is like the basic overview of the whole deal. There are really, truly a lot of implications to this. Also, it's a good, like, nice kind of problem to know how to solve. It's generally on an exam when we generally give an exam, which will happen. So we're going to practice this. It's something worth practicing. That's what we're going to do in a second. But so last thing, again, the Doppler effect, sort of classic example, at least in New York City, is by which I mean high frequency as the thing's coming toward you, then low frequency as it goes away from you. Again, a lot of people think that other things are going on there. I mean, other things are going on, like volume stuff, but that's not what I'm talking about. I'm talking about what I just said. So now let's do a numerical example. Okay, in the time that we have left. Okay. I'm going to put numbers in here. Just so I think there's four basic, and I mean Doppler effects can be all very complicated and can be two-dimensional, three-dimensional, but look at the basic ingredients of a Doppler effect. The way I like to think of it is you could have the receiver approaching the source, or you can have the receiver receding, or you could have the source approaching, or you could have the source receding. Those are the four basic combinations. And you, of course, you can have both of anything. Like it can get more complicated from there, but those are the four basic cases, and they're worth looking at, you know, in comparison to one another. What generally happens in this class is we're going to fully numerically like walk together one case. I'm going to show you a method for walking through one case. I'm going to tell you definitively that that method is the method used to analyze any case at all. And I'm going to definitively over and over again tell you to use this method, not to just use this one random stupid equation that exists on the web that's really, really misleading and really seems attractive, but will get you into trouble. Anyway, I'm going to show you a method for solving these problems. And I'm going to say that this method, once you understand it, can be used for any case and runs the exact same way as a method for any case, but it's worth. So therefore, in principle, once I show you one case, you could do all the others in principle, but it's worth, we're going to walk through probably two, because it's really worth seeing a comparison of what happens when you compare two cases. And I don't remember if you have a lab day on this or not, but this does tend to come up on the exam. We do tend to ask you to sort of run through at least two cases and make a bunch of comparisons and come to conclusions about them. So this is like practice. Actually, I should ask you, just to check, I don't believe you have not had a motion about this or anything directly in lab about Doppler effect, correct? Could I get confirmation? No. Okay, great. No meaning. Okay, great. Thanks. We have not. Great. Okay, cool. And that is good. That's as it should be. Just making sure. Okay. So in my stupid diagram here, or with the way I do these diagrams, I generally, I make the big blue thing be like a speaker, like it's the source of the wave. Those ripples are supposed to be the wave themselves, and then that stupid ear thing is like the receiver of the wave. Okay. And then I give you some basic facts here, like some givens. Let's assume that the frequency of the wave as measured by the source, let's assume is is 440 hertz. Okay, again, that's a realistic number. That's middle A on the piano. Okay, we're going to assume that. We're going to assume, sorry, I'm running out. Actually, pardon me. Hold on. I'm not changing this. I'm just making it smaller. Hold on, sorry. So what I'm going to assume so far is given, well, there's one of the, Okay, here's the assumptions or the givens. I'm assuming that a frequency is produced by the source, measured by the source to be 440 hertz. I'm assuming that it's a sound wave, so that the sound wave of frequency 440 is traveling through the air, through a medium of air at standard temperature and pressure, and it's traveling, and therefore it's traveling at its standard speed of 340 meters per second. That means VWM equals 340 meters per second. I'm saying that means that the speed of the wave relative to the medium equals 340 meters per second, right? That's how fast the ripples are propagating compared to the air through which they are propagating, right? And then I'm assuming, or as a given, I'm saying, let's assume that this source is standing still so that the velocity, the speed of the source relative to the medium is 0. So put more specifically, I'm assuming that the speaker is standing still in the air compared to the air. Conversely, I'm also assuming that there's no wind or something like that, right? So the speaker is just sitting here in the air. Put another way, I don't care really whether the speaker is sitting still relative to a room or not. I don't care if the speaker is like on a train and the train is moving past the station. Like none of that is interesting to me. The issue is what the speaker is doing relative to the medium for this wave. And I'm asserting that this speaker is just sitting still in the medium for the wave. But now we've got an ear, a receiver, an ear that maybe is in a car or something. And this ear is going to receive this sound. The ear, for whatever reason, is approaching the speaker at a very high speed. I mean, 80 meters per second. These are realistic numbers, but 80 meters per second is very high. That's like, and I'm making it high to make the number somewhat dramatic. That's like 180 miles an hour. So that ear is like in an airplane or something, or maybe a train. So it's not wildly unrealistic, but it's not like everyday number. The other two numbers are totally everyday numbers. So the setup, so you see why I call this case receiver approach. This happens to be a case where the receiver is approaching the source, and our question, the question of the question is going to be using these numbers. We're going to solve for the frequency of the wave relative to the receiver. Okay, that's what we're going to solve. That's the goal here. I can tell you right off the bat that I think you could, in fact, tell me right off the bat that the answer that we're going to get, I mean, I don't literally numerically know the answer. There's going to be an involved calculation, but I can tell you that the answer is going to be higher than 440 hertz. I hope that's clear from what we were talking about before. Like the ear is running into the waves, so it's going to receive those waves at more frequently than the rate at which they were sent out. It's going to hear a higher note, and we're going to solve for what that frequency is going to be. Is there anything else I'm left out? Oh, okay, so we're going to start solving. One thing you'll notice, I'm starting to write all these measurements, particularly these velocity measurements. I'm starting to write them with double subscripts all the time. That's a habit that is a really important one to get into. In principle, I should be in that habit throughout all of physics. I should always use double subscripts after velocities, but it's particularly important here. The reason for that habit is that, as I was saying before, velocity is a relational concept. Velocity is meaningful only as a relation between two objects. Velocity as a property of one single object is meaningless. In other words, it doesn't mean anything to say, okay, how fast is the Earth actually moving? Like, I know the Earth is moving past the sun, but I know the sun is moving past the Earth, but I know the sun is moving past the galactic center, but I know the Earth is like sitting still relative to my feet, but like really, like actually, like what actually is the Earth doing? Like in space, like by itself? That is not a meaningful question. The cornerstone of physics is the realization that that is not a meaningful question. The Earth has velocity only insofar as you compare it to something else. And that is true of all objects. To have a velocity, you must be compared to something else. Once you pick the thing you're comparing to, your reference frame, then you get a velocity number. But change your reference frame and you'll get a different velocity number. And all reference frames are equally valid as long as they're constant. Like the laws of physics are true at all constant velocities. That is Galileo's principle of relativity. It is the principle that says we can believe that the Earth is going 65,000 miles an hour past the sun while we sit and don't feel a thing, right? Velocity is relational. Now, what I'm going to do on the next page is write down that, and that's going to play out here in the Doppler effect. Velocity is relational. I'm going to write out a mathematical way of saying that, something that I call Galileo. And I'm going to ask you, well, I'm going to write it out. Well, here we go. In fact, I guess I wrote it on the front page of the notes, but this is just one tidy way of saying, well, I'll let you copy it for a second. Hang on. I'll let you know. It's getting confusing. What's happening? Okay. Oh, chat. Oh, yeah. Great question. Wait, sorry. So, wait. So I don't know how long ago Shasha put this in the chat. I'm sorry. I mean, the answer is yes, and I'm totally going to get to that. I'm not sure if you put it. Oh, 522. I'm not sure if you put that in. Yeah. Oh, okay. But I'm totally going to talk about direction. Yes. Really good question. Hold on, everybody, 1 second. Pardon me for 1 second. Okay, in brief, what this is saying, so yeah, and in fact, that's great. Yeah, velocity is a vector quantity. It does deal with direction. We're going to have to worry about direction here. And in fact, yeah, and maybe this is the reason Shasha said that. I'm not sure, but that's why I put the arrows above the V's in this state, in these three statements here. I'm saying that this is a way of mathematically reinforcing that velocity is a vector. It does deal with magnitude and direction, but it does so in a relational way. What it's really saying in short right here that we're going to need for the Doppler effect is, if you have any three objects, A, B, and C, like moving at like random, distinct, constant velocities, if you want to know the velocity of one object relative to itself, you're always going to get zero. The velocity of, like, in other words, the velocity of a single, oh yeah, sorry. Yes, awesome, right. Oh, you guys get put, now you guys get point, yeah. The velocity of a single object is always zero. You need another object to compare if you're going to come up with any number other than zero for velocity. So V of object A relative to A is always nothing. VAB is always something, but just for the record, it's symmetric. What it's saying here, statement number 2, VAB is always equal to negative of VBA. We're going to use that here. I mean, I don't know if that's obvious or not, but like, if the Earth is going at 65,000 miles an hour to the east past the sun, then the sun is going 65,000 miles an hour to the west past the Earth, always, necessarily, right? So one object, you can't do anything meaningful with velocity. Two objects you need to do something with velocity, but what you're going to get is something always symmetric, mirror image. Once you have three objects is where velocity gets interesting in a way, and that's what we're going to deal with here. What the third statement says is, once you have three objects, A, B, and C, then you can see that velocities begin to add. They add in a meaningful way. They add like vectors. Yes, velocities add precisely like vectors, as in if they're two-dimensional, their components will add up. And if there were arrows, you put them tip to tail, they totally add like vector. And negative signs matter, direction matters, just like vectors. But specifically, they add in this way that requires you to pay attention to their frames of reference, to the comparison. That is to say, what this is saying here, and I say it somewhat quickly to get back to the Doppler effect, but what this is saying is the velocity of me relative to the subway plus the velocity of the subway relative to New York City streets gives me the velocity of me relative to streets. That's why I take the subway, right? Because I can have a velocity of 0 relative to the subway. I can sit and chill on the subway and I'm going 0 relative to the subway. So the seat is like right always there at my leg. And you know, the person who's next to me is like always next to me. I'm going 0 relative to the subway, but the subway is going 85 miles an hour relative to Brooklyn. Therefore, I am going 85 miles an hour relative to Brooklyn, right? In the simple case of a one-dimensional situation with zeros involved, we rely on this all the time. What physics is saying is that this is true all the time, even when it doesn't seem obvious, even when zeros aren't involved, even when negative signs or two dimensions are involved. I mean, in the case of a negative sign is, you know, you can run up the down escalator, right? And the velocity of you relative to the escalator plus the velocity of the escalator relative to the mall gives you the velocity of you relative to the mall. And if you do things right and you arrange your negative signs right, you can run up the down escalator at the same magnitude of velocity as the escalator and then not be moving at all relative to the mall. Is there any chances it will have? No, then you would just do, we'll never have a situation with 4 objects. We would just do this. Like in life, there can be many objects, but we would just do this over and over again. No, you never have to worry about 4 objects. So in fact, with that, got it, okay. So we're going to use this, and we're saying this is true. What I just wrote here, hopefully it sort of seems obvious, maybe, but I'm saying it's always true about velocities, always. And all velocities are relative. When it comes to a wave, the velocity of the wave that we know in advance, the velocity of the wave that we rely on to be fixed and determined and constant is the velocity of the wave relative to the medium, right? But now we're going to see how that pans out. in the case where something making a wave or something receiving a wave is not stationary relative to the medium. So here we go. So our goal is to take the situation of the numbers that I just gave you, and we're going to solve, and we have sort of limited time, so I'm going to do this sort of fast because I do want to finish this one case by yeah, we've got, okay. So I'm going to be a little bit fast. I apologize, but I want to get through it and have you do this one, see this one case before we're done. So remember our, right, we're solving for the frequency of the wave as measured by the receiver. We believe correctly that it's going to be higher than the frequency of the wave as measured by the source, which was 440. One thing. Okay. Okay, before we do anything else, we totally want to address, I think it was Kwan's question or Shasha's question, both. I want to address directionality. We're going to be doing things with velocities here, adding them, subtracting them, if we worry about velocity. So before I go any further, and the laws of physics are the same in all coordinate systems. So let me choose a coordinate system. Let me assign. In other words, the first thing I'm going to do in any case of any Doppler effect problem is I'm going to look at the situation. I'm going to decide what direction I'm calling positive and what direction I'm calling negative. And I'm always going to, you can do whatever you want as long as you do make a choice and are consistent with it. But my strategy is I'm always going to assign the direction in which the wave is going as positive. I'm going to assign the wave as positive, like the direction that the wave is going from the source to the receiver. That way, when I say that the sound travels at 340 meters per second, I really can say positive 340. Like that's the way the wave is going. I'm going to call anything that goes that way positive. Therefore, right from the get-go, I'm going to say, therefore, this thing here, the receiver that's coming in, it's going against the wave from according to my coordinate system, that's going to be a negative, right? Okay, like it wasn't given in the problem, but I'm making that decision now. I'm saying anything going against the wave is negative. All the other numbers are positive. Okay, so that's the first thing I do in every Doppler effect problem. Then from then on, I have a three-step method, which again, I'm going to do a little bit quickly here. But I have a three-step method that works for all the different cases. Step one is use the frequency as measured by the source to compute the wavelength as measured by the source. So here we go. One thing I forgot to remind you, I mean, we made a big deal of this last week and you made a big deal of it in the lab. Everything I've been saying about velocity is true of velocity in general, but we specifically have a wave here. So specifically with waves, the velocity, the speed of a wave is always its wavelength times its frequency, right? We made a big deal of that a couple of weeks ago. That's always true of all waves. It's not relevant if you don't have a wave, but if you have a wave, it's relevant. So that's true. And so now we're going to like apply subscripts appropriately to that. In other words, I'm going to solve for lambda. So the velocity of a wave is equal to the wavelength times the frequency. And if the laws of physics are true in all reference frames, then that would be true. And that's certainly true according to the source. So the velocity of the wave relative to the source equals the wavelength of the wave relative to the source times the frequency of the wave relative to the source. And I'm telling you, and you'll see why I'm doing this in a second, I'm solving for the wavelength. So I'm going to say wavelength of wave relative to source equals velocity of wave relative to source divided by frequency of wave relative. Like, no big deal, right? I'm going to solve for the, and it seems like I have what I need to do this. Well, I certainly have the frequency of the wave. So I'm solving for the wavelength. One thing, so I'm just going to okay, again, I'm going to have to do this a little bit faster. You got 7 minutes. I'm solving for the wavelength according to the source. It's velocity over frequency. The frequency of the wave, according to the source, was explicitly given. That's 440 hertz. That's not an issue. VWS is not explicitly given. What's given is VWM. That is to say, I know how fast this wave is traveling relative to air. It travels at 340 meters per second. Explicitly, nobody told me how fast it's traveling relative to the speaker. You might say, well, duh, I mean, the speaker, I mean, isn't it traveling 340 meters per second relative to the speaker? Yeah, it is, because what you're saying is, you know that the speaker is just sitting in the air. Therefore, whatever the sound is doing relative to the air is what it's doing to the speaker. You're kind of saying, you're right that whatever the sound is doing relative to the air is the same as what it's doing to the speaker, because what you're in effect doing in your head is saying, I don't have to, I can take into account the speaker, but there's not much to take into account. In other words, what I'm saying is this. I'm saying this. What we know is that VAC equals VAB plus VBC. We know that the speed of me through the streets equals the speed of me relative to subway plus subway relative to streets. And we know that's an easy calculation when one of the numbers is 0. But let's recognize it's a calculation and one of the numbers is 0. In other words, we're saying and I apologize, I'm going a little fast. I can turn back the pages if you want, but I'm saying we know that VWS is VWM plus VMS. It's the velocity of the wave relative to the medium plus whatever velocity the medium might have relative to the source. Now it happens that we know that the velocity of the medium relative to the source is nothing. There is no wind or anything like that, but that's not always true. But we know it here, it's 0. So I'm explicit. So I'm saying, to be explicit and clear, what I'm saying is, velocity of the wave relative to the source, really what it equals is the velocity of the wave relative to the medium plus the velocity of the medium relative to the source all over the frequency of the, and forgive me again, I'm going to be speeding up a little. Again, I'm going to post the notes and all that, but I do want to get you through this. So we have that, and we're saying this is 0. So we're saying yeah, so the thing that was written below the VWS here. Oh, here. FW, sorry. Yes. FWS, like frequency of wave relative to source. Okay. Got it. Okay, so I'm going to go back. Got it. So it's F. Okay, I'm going to go back if that's okay. Because okay. All right, so we've got this. So the wavelength of the wave relative to the source equals that, which is Now, and I know we only have a couple minutes. Why'd I just bother to go through this? Okay, great. Thank you. Thank you. Why'd I just get the wavelength? Because here's step two. Step two is nice. Step two is recognize. The reason I'm always going to solve for the wavelength first, always, in every single case, I'm going to get the wavelength according to the source first, because that's the one thing everybody in the situation will agree on. The wavelength is not going to change from the source to the receiver. However far apart the ripples are, they are, and they're going to stay that way as the wave travels from the source to the receiver. So if I can get what the wavelength is according to the source, which I just did, now I can do step three, and there's only one step left. So just bear with me. And if you have to go, just go, but I'm going to finish this. So if I go 2 minutes over, I apologize. You can go, or you can watch a recording later, but I will just stay here to get this done for everybody. And really, we're on step three now, which is the last step. Step three is we're literally going to run exactly what we just did in reverse. It's almost going to look like a circle, but it's not going to be a circle. We're going to use this wavelength for the receiver to compute our final thing that we're looking for, to compute FWR. And how we're going to do it, we're going to do the exact same thing. We're going to say FWR must equal VWR over lambda WR. We're literally just doing what we did in step one, okay? But then we're going to say to ourselves, what's VWR? Do we know it? We don't explicitly know it. We know VWM. What we know is that VWR must be VWM plus VMR, you see, just like we did a second ago. And this time it's not going to be a zero, right? What we know, VMR must equal the negative of VRM. VRM, we said, was negative 80. So it's negative 80. Right, I'm going fast, but what I'm really basically saying is, if we know that the receiver is going into the air at negative 80 meters per second, then the air is going at the receiver at 80 meters per second. The air is blowing toward the receiver in the same direction as the wave, hence positive, at 80 meters per second, right? And that's relevant. That's going to, so I'm going to plug that in and we're going to be done. We're one step away. So I'm saying FWR equals VWM plus VMR over WR, and that is 340 plus 80 all over the 0.70, and what we get, well, 420 over 0.77. And we get, well, approximately and this is the answer, and we're done. And if you have to go, go. But just to summarize, that's the answer. 545 hertz. Notice it's higher than 440, just like we predicted. In fact, dramatically higher. And notice all we did, we used frequency to get wavelength at the source. Then we said, oh, that wavelength is the same at the receiver. So then we used wavelength to get frequency at the receiver. We just did the same equation twice in reverse. It's just recognizing that the receiver and the source don't actually agree on the velocity of the wave. The wave is always going at 340 meters per second relative to the medium, but not everybody in town is going zero relative to the medium. So somebody experiences a different wave speed, therefore a different wave frequency, and we're done. I will hang out if there's any questions. Oh, 1 minute over. Okay, thank you for being so indulgent and letting the whole thing go. Thank you. Have a great, okay. And I'm not going.
Can you go back to the others? Can you go back to the last slide for a second?
Absolutely. But thank you, Grisella. Thank you. Yes, yes, sorry. Yes, sorry. Okay. And thank you, guys. Yes.
Thank you.
Thank you. Awesome. Oh, great. Oh, thank you, guys. Yes, have a great rest of your. Thank you. Have a good. Thank you. I know that was great. Okay. Thank you. Thank you. Oh, thank you. Great. Okay. Good job. Good job.